Okay, these will be the last examples of the disc or washer method. What you see over on the right here are the two graphs graphed on a graphing calculator window of 6 minus 2x minus x squared and x plus 6. Okay, so we're going to take the region bounded by these two curves and we're going to revolve them first around the x-axis on this page. So let's color in the region, figure out what the shape would look like. Now before I draw my mirror image, I kind of want to know where this intersects. Maybe I'll make it a different color. So how are you going to figure out where that intersects? The same way you would in an algebra class, where you want to know where y equals this and y equals this, where do they hit each other? That would be where they cross. So since y equals 6 minus 2x minus x squared and y equals x plus 6, then the two of those must equal each other at the points of intersection. Okay, so you solve this, pause this now, solve it, and we'll meet up here as soon as I'm done. Okay, so that's as far as I went. I moved everything to the right-hand side. Then I factored out an x, and I got x equals 0 from this one, and I got x equals 3 from this one. And I just labeled the points, 0 something, negative 3 something, because that's what I got when I set that equal to 0. I could get the y values at some point if I want. Right now, by plugging it into either one. So you could see that would be negative 3, 3, and that would be 0, 6. But for right now, I'm just going to leave the picture labeled how I have it. And now I'm going to start my examination of what I need and maybe draw the rest of my picture. So I think I want to make my mirror image start, I guess, right in the middle of my work there. And maybe right about here, right? And there's my line, and there's the shape. Probably isn't that, great as far as how far away it is, but you get the picture. Alright, so here's my inner radius, and I can draw as many of these as I need to until I realize, okay, my inner radius is a y equals. So y equals a function of x. So that's a little radius of x, and that's going to equal my x plus 6, because this is getting kind of junky. Alright, now let's do the outer radius. The outer radius, you can see, goes to the curve. Okay, so that's going to be my big radius, and again, my big radius goes to the curve. So that's the 6 minus 2x minus x squared. And I apologize for the complete and total mess. Alright, yeah, Kelly and Marissa, you guys would never have something this sloppy. Nor would a lot of other of you. Okay, so now we're going to integrate pi times the integral of big radius squared minus little radius squared. Big radius. Now, keep in mind that the axis of revolution is just the x-axis. It's not a shift of any kind. So we didn't really have to think too hard about the radii. They're just the function. Big radius squared minus little radius squared. And look at your x bounds. That's why that was the only thing I even labeled were my x numbers. So I wasn't even tempted to use the y's. And I'm going to let my calculator integrate this for me because I know it's going to come out to be a rational number. Okay, hopefully you paused to give yourself time to get the answer. If not, do that now. You should have gotten 243 fifths, and then don't forget to put in the pi. Alright, next we're going to go around the line y equals 3. So again, I'm going to shade this in. Now you remember the points of intersection from the last page. Now I will go ahead and put in the y values. Again, if you plug in a negative 3 here, negative 3 plus 6 is 3, so that's where I'm getting my y value. And then 0, 6 is my y value. And the reason I actually wanted to label my y's now was so that I knew where to draw in my axis of revolution, which it's right there. And I know it's right at my intersection point. So now I know how to draw my mirror image. That's good enough for me. Alright, I still always like to draw the radius or radii from the axis of revolution to the shaded part. Now, again, I have an inside of the shaded part. You know what I'm going to do since I'm using yellow? I'm going to make that to the outside of the shaded part. So my yellow is going to be my outside radius, and let's pick a different color for my inside radius. Because I just want to make sure that I see my inside radius is my line, and my outside radius, make this a yucky yellow, my outside radius, yes, it kind of looks yellow in my color picker, is the trinomial. Now, did I do this right? Isn't that what I had for my radii for the last problem? Okay. When actually, this orange, the x plus 6, doesn't that really measure all of that? And I guess I should try to be consistent with the colors. That really measures all of that, right? What I don't want, though, is I don't want this part. So since I don't want that part, I'm going to subtract 3 from it. Same thing with 6 minus 2x minus x squared. Really measures this whole thing. But I don't want this part. So from here, I'm going to subtract 3. Now I have my correct radii for this particular volume of solid of revolution. So let me set it up. Volume equals pi times capital R squared. Now I am going to combine those like terms. So 3 minus 2x minus x squared, outer radius squared minus inner radius squared. And x plus 6 minus 3 is is x plus 3. So integrate this whole thing with respect to x from, and my x bounds, because it's still a horizontal line, I'm still using x's, and I am still going from -3 to 0. So pause this, get it on your calculator, and we'll check answers, or compare answers. Okay, and you can see the answer is much smaller, which it should be, right? You cut out a whole lot of this actual shape whenever you weren't swinging it nearly as far around. So this answer is 108/5 pi. So that's the end of these videos as far as washer method, disc method. Hopefully you kind of have a handle on these. And on the next picture, I'm going to make something up, and I want you to start thinking ahead of the next thing that we're going to do. All right, let's say that we want to take this region this time, and we want to swing it around the y-axis. All right, if you want to swing this around the y-axis, probably the shape isn't that hard for you. There's the line. Okay, it's not that hard to envision. It looks like some angel wings before I swing it around. Okay, let's see. So, from the outside it would look kind of like, I don't know, closed up bundt cake, and then you have this big cone taken out of the bottom, okay? Now here's the thing. Because I'm going around a vertical axis of revolution, all of the formulas you have so far integrate this with respect to y. The second thing is, if you think about inner and outer radii, I just drew an inner radius and an outer radius that are hitting two pieces of the same function, right? I'm hitting the inside bump of the curve, and then I'm hitting the outside bump of the curve. Both of these things together are giant problems, okay? The first is coming up with an inner and outer radius, and again, now if I come up with an inner and an outer radius down here, that's definitely a bad color. The inside radius hits the line, and the outside radius hits the curve, so at least that's a little bit easier to deal with. But again, up top in the bump part, that wasn't the issue. The last problem to reiterate is the fact that if I'm going around a vertical axis of revolution, as of right now, I'm supposed to have everything in terms of y. This one's not bad to get in terms of y, right? But how about this one? You want to solve that for x in terms of y? Now, at least in this one, it's possible, but you would have to complete the square. It's not going to be fun to get the x by itself. And then you have to figure out where you're actually splitting this up as far as the two different functions of y you would get, because you would get a plus or minus square root. So, and in some functions, it's not even possible to solve this thing for x. Okay, if this was y equals x sine x, you wouldn't even be able to solve it for x. So there is another method, and it's called the shell method. So if you guys want to look ahead, check out YouTube for shell method. If there is a con video, which I would imagine there is, look at that before class. It might help. And I'm going to go over the shell method on Monday. That's what we're going to do on Monday. And I might put a video or two out. So here's the homework, all of the homework if you haven't gotten it all, which I think you did. And then I do have to get you the page from the Larson book. Okay, hopefully you watched this before the weekend, or it is the weekend. So have a good weekend, or continue to have a good weekend. Again, this stuff and the shell method we will go over next week. We'll start in class, plus I'll throw up some videos.